We are almost ready to build a quantum field theory for scalar fields using many-path approach. First, let us write the action. That's for an evolution of the field over a finite time t. However, the field extends spatially over the whole space, so we have an integral from -infinity up to +infinity for the space part. Therefore, we have an asymmetric treatment of space and time because the integrals do not have the same boundaries. For that, we first shift the origin of time, and then we extend t to infinity. This way we can rewrite the action as a space-time integral over infinite boundaries of the Lagrangian density. So from now on we are only going to consider evolution of the field over an infinite time, so from far in the past until far in the future. Now, in order to write our quantum field theory starting from the many-path approach, we will process by analogy with what we did in quantum mechanics. So in quantum mechanics we had an amplitude of probability for a particle to go from an initial position qi, ending up in a final position qf over a time t. And to get that we had to use the evolution operator exponential minus iht, where h is the Hamiltonian. And what we did was to rewrite that as a many-path formulation with a path integral, where we have to sum over all the possible paths connecting qi and qf over a time t, and what we are summing is exponential I times the action for each of these paths. We know that in field theory the dynamical variable is not the position q anymore, it is the amplitude of the field. So let's write a similar amplitude of probability as in quantum mechanics, but by replacing q by phi. Here there are a couple of quantities we need to define. What is the state of a field, and what is a Hamiltonian in field theory? In quantum mechanics, the state of a particle is its position, and in fact it can be in a superposition of different positions. The state of the field is defined by the amplitude of the field at each different position in space. Take for instance the temperature in a room. That's an example of field because the temperature is a function of space and time. The distribution of temperature at a given time in a room will define the state of the field temperature. Of course, we are used to experience temperature as a classical field. That means that at each point of space we have only one value for the temperature. If it was a quantum field, however, we could have a superposition of different temperatures. So the room could be cold and warm at the same time in quantum field theory. In principle, to describe the evolution of a quantum field, I will need the evolution operator and therefore a Hamiltonian for the field. We will be able to express the Hamiltonian for a field when we will discuss canonical quantization. However, a difficulty with canonical quantization is that it does not treat space and time explicitly in a symmetric way. We see that by looking at the evolution operator, which contains time but not space, and that's because the Hamiltonian is the generator for time translation. This is a problem we don't have in the many-path formulation, in which it is easier to impose a symmetric treatment between space and time as long as we have an integral over time and an integral over space which has the same boundaries as discussed earlier. So let's write a path integral for the amplitude of probability associated with the evolution of the field by analogy with what we did earlier in quantum mechanics. The path integral is summing over all the possible evolution for the fields, connecting the state of the field phi I with the state of the field phi f over a time t. But we already discussed earlier that this time needs to be infinite if I want to have a symmetric treatment between space and time. So let's take t goes to infinity. We now need to pause a little bit and think of what it means, evolution and a path for the field. In quantum mechanics we wrote the path in a diagram representing space and time. We had our initial and final events, and to get our amplitude of probability to go from the initial event to the final event we had to sum over all the possible paths connecting these two events. But now our dynamical variable is not space anymore, it's the amplitude of the field at a given position of space. Remember that I have an infinite number of dynamical variables, the amplitude of the field at each point of space. This means that we have a path integral at each point of space. And what is a path? It's the evolution of the amplitude of the field at this point over the time between the two events I am considering. So mathematically, the path integral in quantum mechanics is already a very complicated object. But in quantum field theory, it's even worse, because the path integral for a field is actually an infinite number of path integral we had in quantum mechanics. So it's usually a formidable task, if not impossible task, to try to solve quantum field theory directly using the path integral formalism. The good thing is that there are cases where we can solve this path integral analytically. That we will see is a case when we have free fields, and we can also solve it approximately, for instance using perturbation theory, using Feynman diagrams. But before we get there, we will massage our path integral a little bit to have a more convenient form. And what we will do in particular is to consider the initial and final state of the field to be the vacuum. The vacuum for a field can be a very complicated object, in particular when there are interactions happening. However, our definition of the vacuum here is a very simple thing. Essentially, this is the amplitude of the field being equal to 0 everywhere. And by analogy with the partition function of statistical mechanics, we will write our amplitude with the letter Z. This doesn't look very promising, because what we have is a path integral for a field, which is one of the most complicated objects we can think of, and we are going from nothing to nothing over an infinite time, so a priori a very boring object. But thankfully some physicists in the past have found some very clever way to make this object interesting and useful, and that will involve sorcery.